Section 2.8 is proportions and similar figures. I can find missing lengths of similar figures, and I can use similar figures when measuring indirectly. Those are our learning targets today and what we're shooting for. Big ideas here. Proportional relationships can be used to find the missing side lengths in similar figures. Such figures can be used to measure real-world distances indirectly. This little symbol here means is similar to. It's kind of like a little wavy dash. Means is similar to. And if we look at page 130, there's some more information there. Here it tells us triangle ABC is similar to triangle FGH. That means that the corresponding angles are equal or congruent, which is an equals with our little similar line on top. And corresponding side lengths are in proportion, which means the ratio of them are the same. The order of the letters when we name a particular when we name similar figures is important. It tells us which parts of the figure are corresponding parts. So triangle ABC is similar to triangle FGH. That tells us A and F are corresponding, B and G are corresponding, and C and H are corresponding. So the order here does matter when we name these. Example 1 is finding the length of a side. So in the diagram below, this is also on page 131 with a little bit better pictures, we want to know what is DE. Right now we don't know, but we do know that triangle ABC is similar to triangle DEF. And they told us this in the book as part of the problem. So we know then that since these are similar, DE and AB have to be similar, corresponding parts. So we can see this in our diagram because our sides are different enough that we can tell. But if you can't, always look back to what we know here. So I can set up proportions here. And remember, when we set up proportions, it's important that we're comparing similar things in our numerators and in our denominators. So I'm going to have one that's from my big triangle and one that's from my little triangle. We also need to have a set of values that we know in both. And if we look here, I know my upper right side, BC and EF, and these are corresponding parts, BC, EF. So since I know both of those, I can use this relationship to help me figure out the other relationship. So in my big triangle, I know this side is 16. In my little triangle, I know that corresponding side is 12. So I'm putting the side I know in the numerator. The side that I don't know that I'm looking for, I'm going to put in my denominator. And it wouldn't have mattered which one we put on top and which one we put on bottom as long as we're consistent. So I have 10 here, and we don't know DE, so I'm going to put an X there. We also can compare just our side lengths. So I could have done like 16 over 12 and 10 over X. It doesn't matter, again, as long as we're consistent. So here I have big triangle, known, over unknown. And I know that we know the 10 here, but it's like right and left. Now that we have our proportion, we can solve it. In order to solve proportions, we cross multiply. So I take 16 times x equal to 10 times 12. I get 16x equals 120. Divide by 16. And x here is going to be 7.5. Last thing we want to do is check and see, does our answer seem reasonable? Well, 12 is less than 16, and 7.5 is less than 10. And they have a comparable relationship. They're both 3/4 of that length. So, it does seem reasonable. Now, feel free to pause here and give this a try if you'd like. Using those same triangles from above, we want to know what is AC. So here, I'm looking for AC, and I compare that to DF, the bottom on both of them, or AC, DF is corresponding from the way that they labeled their triangles. So I'm going to set up my big triangle compared to my little triangle, just like I did in the first example. And we know that these are similar, so I can set my proportions equal to each other. Again, I'm going to use the one that I know both pieces of, and now we know this is 7.5, so we could use that one if we wanted, but I'm still going to use the 16 and the 12. So I know 16 in the big triangle, I know 12 in my little triangle. I'm looking for AC. That becomes my X, and the 18 I know in my little triangle. So right now it's like I have right over bottom. Right over bottom. We compare the same triangle in the same order. And that's important here. Now, I can solve my proportion by cross multiplying. And since our proportions or our ratios are equal to each other, we set our cross products equal to each other. Here I get 288 equals 12x. To get our x by itself, we divide, and I get 24 equals x. Double check, does that answer seem reasonable? Well, I know it should be bigger than 18, and it's in that same 4:3 or 3:4 relationship that we talked about with our other side. So yeah, our answer seems reasonable here. In example 2, again, there's a figure on the bottom of page 131. I put a rough sketch of it up here, but the one in the book is better. The sun's rays strike the building and the girl at the same angle, forming two similar triangles shown. How tall is the building? Well, we know the height of the girl is 5 and the length of the shadow is 3. We don't know the height of the building. That's what I'm looking for. But we know the shadow is 15. So I can compare the girl to the building. Those are the two pieces we have, and of them we know height and shadow. So I'm going to compare height to shadow. The girl's height is 5 and her shadow is 3. The building's height we don't know, but we know the shadow is 15. Height, shadow, height, shadow. And we don't know that height, that's what we're looking for. How tall is the building? Now, here, when we solve, we have two options. Because my variable's in my numerator, I can either just multiply both sides by 15. Remember, it's 15 over 1. We multiply fractions straight across and get 25 feet. Or, again, I could have used cross products here, which we can always do with proportions. Simplify, solve for our x, it's being multiplied, we're going to divide, and still get to 25 feet. Give this a try, please. A man is 6 feet tall, standing next to a flagpole. The shadow of the man is 3.5 feet, and the shadow of the flagpole is 17.5 feet. What is the height of the flagpole? I drew a rough sketch here, not to scale, and my flag doesn't have the right number of stripes, but we're just going to go with it. It says our man is 6 feet tall, and the shadow is 3.5 feet. The shadow of the flagpole is 17.5 feet. And since it hits at the same angle, these are going to be similar triangles. And we're looking for height of the flagpole here. So again, I can compare the man to the flagpole, and I compare heights to shadows, or shadows to heights. That part doesn't matter. We plug in what we know. The man's height is 6 feet, and the shadow is 3.5. The flagpole's height, we don't know, and the shadow is 17.5. So we can solve this with proportions by cross multiplying. So I'm going to take 6 times 17.5 equal to 3.5 times x. Again, we set our cross products equal to each other. Here when I multiply, I get 105 equals 3.5x. Remember, we have to simplify each expression before we can solve. Now my x is being multiplied. We get rid of that by dividing, our inverse operation there. And x is going to equal 30 feet, which seems reasonable for a flagpole. A scale drawing is a drawing that is similar to an actual object or place. Floor plans, blueprints, and maps are all examples of scale drawings. In a scale drawing, the ratio of any length on the drawing to the actual length is always the same, and that ratio is called the scale of the drawing. So in example 3 here, we're going to interpret scale drawings. Using the map on page 132, which I have a picture of here, what is the actual distance from Jacksonville to Orlando? So here, I have our scale as 1 inch to 110 miles. So here I'm comparing the map distance to actual distance. Okay, in my scale, and then for this particular problem, so from Jacksonville to Orlando. Well, on the map, it looks like we have 1 full inch and an extra 1/4 of an inch. So 1.25 inches from Jacksonville to Orlando. And we want to know what is the actual distance. So again, my scale is 1 inch to 110 miles. So I put map over actual for both my scale and for what I'm looking for. We can use cross products to solve here because I have a proportion set up. 2 ratios equal to each other. So I'm going to take 1 times x equals 110 times 1.25. We're going to simplify both sides here and get approximately 137.5 miles. And my label's in miles because my map scale is labeled in miles, which seems like a reasonable distance. Now, feel free to pause and give this a try. The distance from Jacksonville to Gainesville on the map is about 0.6 inches. What is the actual distance from Jacksonville to Gainesville? So again, it's the same map. Jacksonville to Gainesville, it's telling us is about 0.6 inches. So we're going to use the same scale here, 1 inch to 110 miles. I have 1 inch to 110 miles. This is my map. This is my real life, or my actual. I set it equal to, on the map, I have 0.6 inches for what I'm looking for. Now we want to know what is the actual or real life distance. Again, we have proportions set equal to each other, so we can cross multiply, set our cross products together. 1 times x equals, because our proportions are equal, 110 times 0.6. When I do this, I get x equals 66 miles. So it's about 66 miles from Jacksonville to Gainesville. Keep in mind that sometimes roads curve and things like that, and our measurement might not be exactly 0.6, but a rough estimate is 66 miles. And I'm going to stop here and I'll do the last example in another video.